Earthquakes around the world concentrate mostly along the boundaries of tectonic plates. The largest earthquakes occur on the highlighted plate boundaries called subduction zones, like the one offshore Japan. Here, the Pacific plate moves westward towards Japan at a rate of 9 centimeters per year. A cross-section through this region reveals the structure of the subduction system, showing the Pacific plate descending underneath the overriding plate on which Japan sits. The plates are made of elastic rock, and the asthenosphere beneath them consists of rocks that are elastic on short time scales while flowing viscously at the time scales of years. Over longer geological time scales, the subducting plate sinks slowly into the asthenosphere. To see how earthquakes fit into this picture, we zoom in on the region around the plate contact, and we also slow down our clock to focus on processes occurring over much shorter time scales. When we do this, we can recognize 4 distinct stages of earthquake cycle deformation. We start in the time period before a major earthquake, called the interseismic period. This interval lasts several decades to centuries to even millennia in some cases. During the interseismic stage, a large part of the plate contact is locked by friction. The subducting plate continues to move at several centimeters per year, causing the overriding plate to shorten and bend downward. Depending on their location, nearshore communities may record this as slow uplift or as drowning of the land. The earthquake happens at 12 on our clock. At this point, stresses have become so high that the plate contact breaks and the two plates slip rapidly past each other. This rapid slip produces seismic waves that propagate away from the fault and may cause damage in the region nearby. This vertical motion of the seafloor may also generate a tsunami, as the water column is abruptly raised and then falls to the sides. During the earthquake, the overriding plate stretches seaward relative to its pre-earthquake position, with uplift near the subduction trench and subsidence near the shore. Let's see the earthquake again in slow motion, but now focusing specifically on the deformation within the Earth. The regular grid is shown for reference. As you saw earlier, the overriding plate slides over the subducting plate during the earthquake, perturbing the grid. The third stage of the earthquake cycle starts soon after the event, when 2 things happen. First, the plate interface relocks. From this point onward, the subduction zone begins building towards the next earthquake. Second, the deeper part of the subducting plate slides into the asthenosphere during a period of months to years. This is commonly referred to as afterslip. During the fourth and final stage of the cycle, stresses produced by the earthquake in the viscous asthenosphere decay away. This post-seismic relaxation phase lasts several decades for the largest events. Once post-seismic relaxation has ended, we have returned to the interseismic stage, in which the surface deformation only reflects the motion across a locked part of the plate interface. We refer to the earthquake cycle as a repeating sequence of these stages, before, during, and after a major earthquake. Satellite geodetic networks allow Earth scientists to measure the minute motions of the Earth's crust and provide key constraints on earthquake cycle deformation. These careful observations are used to unravel what part of the plate interface is locked. This is particularly useful for preparing for large earthquakes in the future. Changes in horizontal surface velocities can be tied to deep Earth processes related to post-seismic deformation. Through these careful observations and models of the subduction system, a great deal has thus been learned about the earthquake cycle.